Namaste everyone. I'm Krishna Karmacharya and today me and my teammate Henry Mahajan will be talking about Markov chains, a concept that allows us to predict probability even when events are dependent, not independent. Let's dive in. Traditionally, probability assumes that events are independent, but Markov questioned if we could do probability even if events depended on the previous one. That's what he set out to prove. To study dependent events, Markov looked at the text. Whether the next letter is a vowel or consonant depends on the current one. So he used 20,000 letters from Pushkin's poem, who was a famous writer. Markov counted the letters and found 43% vowels and 57% consonants. He then looked at letter pairs. For independent events, a vowel followed by a vowel should appear 18% of the time, but he found only 6%. Clearly, letters were independent. To model this, Markov created a predictive machine with states, vowels, and consonants. He calculated transition probabilities based on the data. For example, if the current letter was a vowel, the chance the next is also a vowel is 13%, otherwise, the consonant, which was 87%. Using these probabilities, we can simulate sequences. We start with a vowel, pick a random number to decide the next letter, and repeat. Over time, the ratio of vowels to consonants stabilizes to 43% and 57%, matching the original data. Markov showed that even dependent events followed the law of large numbers. Independence isn't necessary. Today, Markov chains are widely used in the real world applications, like predicting the weather, tracking disease spread, or modeling particle behavior. Markov concluded with a witty line: "Free will is not necessary to do probability." His work was largely ignored at first, but is now fundamental in statistics, machine learning, and many practical applications. After the Second World War, another mathematician, Stanislaw Ulam, contributed to probability in a different way. While bedridden from illness, he spent time playing solitaire. He started wondering, what are the chances of winning a randomly shuffled game? The problem was huge. A 52 card deck can be arranged in 52 factorial ways, about 8 into 10 to the power 67 possibilities. Solving this exactly was impossible. Ulam had a brilliant idea. Instead of trying to calculate everything, he played hundreds of games and counted how many he could win. This gave a statistical approximation of the probability. This approach eventually became the basis for what we now call Monte Carlo simulations. So just like Markov showed that dependent events can be analyzed, Ulam showed that even extremely complex problems can be approached statistically using simulations. Together, these ideas are why probability is so powerful in real-world applications. From predicting the weather to modeling disease spread or even analyzing games and particle physics. In conclusion, Markov and Ulam showed two amazing things. Probability does not require independence, and complex systems can be understood with simulations. From theoretical math to real world applications, probability is everywhere. After recovering from illness, Ulam returned to work on nuclear physics. Unlike Solitaire, here he had to deal with trillions of interacting neutrons. Direct computation of all possible outcomes was impossible, so he asked, what if we simulate the system by generating lots of random outcomes, just like I did with Solitaire? But there's a catch. In Solitaire, each game is independent. Neutrons, however, depend on their past interactions. To simulate this, you need a Markov chain where each step depends on the previous state. They modeled neutrons as a Markov chain. A neutron could scatter and continue, be absorbed and leave the system, or hit uranium 235 and trigger fission, producing more neutrons. Transition probabilities varied depending on neutron speed, energy, and position in the core. The team ran these chains on ENIAC, the world's first electronic computer. They randomly generated starting conditions for each neutron and tracked how many neutrons were produced on average, called the multiplication factor K. After repeating hundreds of times, they obtained a statistical distribution of outcomes. If K is less than 1, the reaction dies out. If K equals 1, it's self-sustaining. And if K is greater than 1, the reaction grows exponentially, which is what makes a bomb. This gave a statistical way to predict outcomes without solving impossible equations analytically. This is how Markov's chain helped in predicting the explosions of nuclear bombs. Now moving on to the modern world. When Yahoo was a trending search engine, at the time it had a critical weakness. Its keyword search was easy to manipulate. Webmasters could simply repeat keywords hundreds of times, even in white text on a white background, to boost rankings. What Yahoo lacked was a notion of quality, not just relevance. In 1996, two Stanford PhD students, Sergey Brin and Larry Page, were working on this problem. They thought of links as endorsements. The more websites linking to a page, the more important that page must be. They borrowed this idea from libraries, where the number of date stamps in a book signaled its popularity. They realized they could model the web as Markov chain. Each page is a state and links are transitions. By simulating a random surfer clicking through links, we can calculate the long-run probabilities of landing on each page. Those probabilities became the measure of page importance. But there was one problem. A surfer could get stuck in a loop of pages. To fix this, Brin and Page introduced a rule. 85% of the time, follow a link, 15% of the time, jump to a random page. This damping factor ensured that all parts of the web could be explored. This method became known as PageRank, named after web pages and also Larry Page. By combining relevance with quality, PageRank produced much better search results, powered entirely by probability and Markov chains. In 1998, they launched their search engine, initially called Backrub. Later, they renamed it Google, a misspelling of Google, the number 10 to the power of 100, fitting their ambition to index the entire internet. Within a few years, Google overtook Yahoo to become the world's leading search engine. Today, its parent company, Alphabet, is worth around $2 trillion, and at the heart of this trillion-dollar empire is a Markov chain algorithm, PageRank, showing how probability can literally reshape the world. Now let's return to Claude Shannon, the father of information theory. He asked a simple but powerful question: can we use probability to predict the next letter or even the next word in a sentence? At first, Shannon tried using only one letter as a predictor, but the results were mostly nonsense. Then he tried using the last two letters, and suddenly real words like way, off, and the began to appear. He realized that more context you use, the better the predictions. Next, Shannon tried entire words as predictors. The sentences were still gibberish overall, but now sequences of 3 to 4 words in a row often made sense. This showed that longer context windows create better prediction. What Shannon was building was initially a Markov chain for language. Instead of pages and links, the state are words, or more generally, tokens. A token can be a letter, a word, or punctuation. Then based on the previous tokens, the algorithm predicts the next one. This is the basic idea behind predictive text like Gmail suggesting the rest of your sentences. Of course, today's predictive systems don't just rely on simple Markov chains. Modern large language models go much further, analyzing massive amounts of text and weighing different tokens differently. But the core idea is still there. Use probability and context to predict what comes next. Not every system can be modeled well with Markov chains. For example, in global warming, more CO2 raises temperature, which adds more water vapor, which raises temperature even more. This feedback loop means the future does not just depend on the present, it depends on the whole history of events. Similarly, if AI models are trained on their own generated text, the system can collapse into repetitive patterns. These are cases where Markov chains fall short. But here's the beautiful part. For many other systems, whether predicting words, simulating neutrons, or ranking web pages, you don't need the full history. You only need to know the current state to predict the next one. This is called the memoryless property of Markov chains. This memoryless property is what makes Markov chains so powerful. It lets us take extremely complex systems and simplify them while still getting meaningful predictions. As one researcher put it, problem solving is often just a matter of cooking up the right Markov chain. We have now reached the end of our presentation. That was a brief discussion on Markov chains, its history, application, drawbacks, and benefits. Hope you liked it. Thank you very much.